So now we look at how to create functions to model real-world situations using this this exponential function idea. So our basic model for the exponential function we're going to use is y equals ae to the rt. You're going to see a lot of this in this video. So we use the basic model y equals ae to the rt to describe many situations where a quantity grows or decays at a rate proportional to its current value. And we've already talked about this. This means that the bigger it is, the faster it grows, or if it's decaying, the smaller the value is, the slower it decays. Okay, so we have, as I said, the basic model y equals ae to the rt. And we've got a couple of parameters and variables here that we have to understand. So E, we know what E is. E is the number 2.718, so on and so on. What's important here? A, the parameter A is going to be the initial value of whatever we're investigating. The initial value when the time is equals to 0, when this model first starts. When the time is equal to 0, whatever the value is at that time, we call this A. Or then, you can see this R is in the power. R is the growth rate or the decay rate. All right, it'll be positive if it's a growth rate. It'll be negative if it's a decay rate. And we'll examine all of these examples anyway. And then T is the time, the independent variable. That would be our input variable T for time and your output variable Y for the value. So how can such a simple setup, how can such a simple function model so many different real-world situations? Well, let's examine that. So here we have a graph of the basic exponential model, y equals ae to the rt. Now in this particular graph right now, a, our initial value, is set at 1, and r, the growth rate, is set at 0.5 or 50%. So let's just examine A first of all. Remember we said A is the initial value. So if we look, A is set at 1 right now, and the initial value right here is 1. When t is 0, the horizontal axis is my t-axis, t for time. The vertical axis is the y-axis, y for the amount at that time. So at time 0, the amount is 1. And that should make sense since our A is set at 1. Now, what if we change the value of A? So if we change the value of A, let's say we make A 2, you can see here on the graph how that affects it. Now the graph starts at 2. When t is 0, our value is 2. And same again, if we continue on and set A up as 3, so now A is 3, you can see our initial value, therefore, is 3. So you can see that changing A, changing the initial value, changes where it cuts the horizontal axis and rises the graph up and down basically. So if I change back to 1 now, set our A at 1, we can see that the graph starts at 1. What about the growth rate? So right now the growth rate is set at 0.5 or 50%. So if we change that, let's say I increase it, make it a 0.6 growth rate or a 0.7 growth rate, you can see that it's growing faster. So my A is set at 1 right now, so that hasn't changed. But as I change the growth rate, you can see that the line or the graph increases faster and faster. And then the opposite is true as well. If I decrease the growth rate, you can see that the graph is increasing slower. What if we set the growth rate at 0? So if we set the growth rate at 0, what do you expect to see? Well, if the growth rate is 0, there's no growth. So then you're going to have a perfectly horizontal line. All right, a perfectly horizontal line. That should make sense because our growth rate is set at 0, so we have no growth. And then depending on, let's move our A up to 2 or 3 for a second. So let's say I have A at 3. What if we include a negative growth rate? What about a negative growth rate? Well, we know we call negative growth decay in this case. So a negative growth rate, we're going to call that a decay rate. And as you can see, a negative growth rate or a decay rate means the values are decreasing. And the more extreme we make this negative growth rate, the faster the values are going to decrease, as you can see here. So what I'm trying to illustrate here is that using this exponential function, this ae to the rt, you can model so many different situations for depending on your values of a and r. So for different values of a and r, you can create an equation or a function that models many different situations. Remembering that a is the initial value when t is equals to 0, and r is the growth rate if it's positive, or the decay rate if it's negative. So now that we've looked at all of the background, let's have a look at an example of a typical question here. So we look at this question 2 here first of all. This is a fairly straightforward, very easy introductory question. So €100 investment gains value by continuously compounding at a rate of 4% annually. Create a model in the form V equals AE to the RT, where V is the value of the investment in euros and T is the time in years. And now we've kind of got two questions. How much will the investment be worth after 5 years? And the second question, how long will it take the investment to double? So in order to figure out how much will the investment be worth after 5 years, and in order to figure out how long will it take the investment to double, we need to create the model first of all, or to create the equation or the function that describes this particular situation. So we're dealing with a function of the form V equals AE to the RT, and remembering that A is the initial value and R is the growth or decay rate. So in this particular question, if I read it carefully, it was €100 investment and it was continuously compounding at a rate of 4%. So my initial value is €100 and my growth rate is 4%. So I have both pieces of information I need. So we can take that right here. So we know that our initial value, A, was €100 and our growth rate was 4%. Now 4%, we're going to write that as 0.04. So we express it as a decimal. Now, a lot of people sometimes ask me, why is A 100? You know, how can we assume that the initial value is always A? So let's just take a look back at this question again. So the question was, it was €100 investment that gains value by compounding at 4% annually. So it was €100 investment. So that means when the time was 0, when this thing started off, when t was 0, the value was €100. So we know that we're taking a model of the form V equals AE to the RT. And if I sub in, well, when t is 0, the value is 100. So let's sub those two values into our function here. So the value is 100. So 100 equals AE to the power of R times, and the value is 100 when time is 0. So R times 0. Now you get 100 equals A times, and this is going to be E to the power of 0 basically. And E to the power of 0 is 1, because anything to the power of 0 is 1. So you get 100 equals A, therefore 100 equals A times 1, so 100 is A. So your initial value, or your A in this particular case, is 100. And that's why we can say, like we say here, A is the initial value, because when you sub in your T equals 0, like I did right here, and put your initial value in for V when t is 0, you'll always end up getting whatever the initial value is will equal A. So sometimes we just skip that step and we realize, okay, A is going to be the initial value. So in this case, A is 100. So now that I know that A is 100 and I know my growth rate is 4%, it gave us to us in the question, creating the function is very easy. We've got V equals 100 E to the 0.04 t. And this is the function that describes €100 investment continuously compounding at 4%. So what would this look like on our graph? So here we have our V equals AE to the RT, and we have a graph here, and on the horizontal axis we've time in years, and on the vertical axis I have the value, which is in euros. Now the particular function that we're interested in is V equals 100e to the 0.04 t. So my A is 100 and my R is 0.04. So we will set our A up at 100 and we will set our R at 0.04. So this is what the function looks like. 100e to the 0.04t, we can see the initial value when t is 0 is set at 100, and it is growing at a rate of 4% continuously every year. So once we have our function figured out, v equals 100e to the 0.04t, we can analyze the rest of the question and try answer the remaining parts. So I was asked, how much will the investment be worth after 5 years? That's what I'm interested in. How much will the investment be worth after 5 years? So we have the function v equals 100e to the 0.04t, and we're interested in figuring out what is the value of v when t is equals to 5. So if we come back to our graph here, we have our graph v equals 100e to the 0.04t, and we're interested in the value of the investment after 5 years. So when t is equals to 5, what is the value of the investment? So this is fairly straightforward. All we have to do is sub 5 in for t as our input in the function. So v equals 100 e to the 0.04 times 5. In other words, v equals 100 e to the 0.2. And all we have to do is put this into our calculator, and you will get v is equals to 122.14. Now remember, this was euros, so it's 122 euros and 14 cents. So we can see here, when t was equals to 5, we put 5 in and our output was 122 euros and 14 cents. So we've answered to part A. How much will the investment be worth after 5 years? We know it would be worth 122 euros and 14 cents. Okay, what about part B? How long will it take the investment to double? So it started off as a 100 euros investment. So when it doubles, it would be worth 200 euros. So once again, we go back to our function. V equals 100e to the 0.04t, and the question this time was, how long will it take the investment to double? So we're trying to solve for t. We know that the value must be 200 euros when it has doubled, and we're wondering what will t be when the value is 200 euros. So if we come back to our graph here, we're saying we know the value is 200 euros. How long will that take? What length of time or what value of t will that be? So in this case, we'll substitute 200 in for v in the function and try solve for t. So what you're looking at right here is an exponential equation. Now, we looked at these a while ago. So remember, to solve exponential equations, we're going to use the natural log. We're going to be getting the ln of both sides. But before we do that, I want to have the exponential on its own with no number multiplying by it. So the first thing I need to do is divide both sides by 100. So I divide both sides by 100, and I will get 2 equals e to the 0.04t. And then I get the natural log of both sides. So the ln of 2 is equal to the ln of e to the 0.04t. And we know that the ln of e to the power of 0.04t is simply just 0.04t. So we have the ln of 2 is equal to 0.04t. Therefore, the ln of 2 divided by 0.04 will equal t. And if we type that into our calculator, we will get t is equals to 17.33 to 2 decimal places. And remember, that was in years. So after 17.33 years, the value of the investment will be worth 200 euros. So on the graph, how long will it take the investment to double? It will take approximately 17.33 years. So this was a fairly straightforward example because we could identify A and also identify R from the question. And we were able to instantly see that the function was going to be v equals 100 e to the 0.04 t by reading the words of the questions, right? Those parameters were given to us in the question. Sometimes we have to do a little bit more work to figure out our growth rate especially. So we're going to look at a more challenging example now.